Okay, today we're going to talk about exponents. And by the end of this lesson, you should be able to say, I can write patterns of numbers in exponential form. Before we get started on exponents, let's look at Pascal's triangle. And this is a triangle of sums. If I look at this, it starts at the top with a 1. The second row would have a 1 and a 1. Now to create the third row, I would add 1 and 1 to get 2, and put my 1's on the end again. 2 1's on the end. To make the fourth row, I would add 1 plus 2 to get 3, and then 2 plus 1 to get 3, and put my 1's on the end. To make the next row, I would add 1 plus 3 to get 4. Then I'd go to the other side and add 3 plus 1 to get 4. And then I would add the 2 3's in the center to get 6 and put my 1's on the end. To make the next row, I would add 1 plus 4 to get 5. Then I'd go to the other side of the triangle and add 4 plus 1 and get 5. And then I'd work with the numbers inside. 4 plus 6 is 10, and 6 plus 4 is 10, and then I'd put my 1's on the outside. To make the next row, I would add 1 plus 5 to get 6, 5 plus 1 to get 6. Then I'd add 5 plus 10 and get 15, 10 plus 5 and get 15, and then I'd add those 2 10's in the middle to get 20 and put my 1's on the end. And this pattern is going to continue forever and ever. I can make a triangle as large or as small as I want, continuing this pattern with Pascal's triangle. And Pascal's triangle is interesting because it's filled with many patterns. Let's look at a few. If I go diagonally, starting with the 1 in the second row, I can add 1 going down. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6. And it also works in the opposite direction. If I move down 1 row diagonally, I can increase by 2, then 3, then 5, because I'm adding 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 4 plus 10 is 5. Then I can continue with the next row, increasing by 3, then 6, then 10, then 15, and so on. Pascal's triangle also has symmetry. If you'll notice the line of symmetry here, all of the numbers in each row are completely reflected across the center of Pascal's triangle. Some patterns in Pascal's triangle aren't very obvious, and one of those we're going to take a deep look into. And this pattern is by looking at the rows and calculating the sum of each row. So row 1 just has a 1 in it, so it equals 1. When I look at row 2, I would add the numbers in that row, 1 plus 1, that gives me 2. I can do that with row 3. 1 plus 2 plus 1 plus 1 equals 4. And the fourth row, the sum would equal 8. In the fifth row, the sum equals 16. In the sixth row, the sum equals 32. And in the seventh row, the sum would be, 64. So let's chart these findings, looking at the row number and how it compares with the sum of that row. What pattern might you notice looking in the column with the sum? You might notice that in each one of these, you are actually multiplying by 2. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, and this pattern would go on forever and ever for as many rows as I wanted to put in my table. So these products can actually be written as products of 2, or these sums can be written as products of 2. So, for example, let's start with row 2, and we'll get back to row 1 in a minute here. But if I look at row 2, I get a sum of 2, and 2 is just 2. 4, though, the sum in the third row, can be written as 2 times 2. The sum of the fourth row, which is 8, can be written as 2 times 2 times 2. The sum of the fifth row can be written as 2 times 2 times 2 times 2. So there are 4 2's being multiplied. And in the sixth row, 32 can be written as 2 times 2 times 2 times 2 times 2. So it's the product of 5 different 2's put together. Notice another pattern here. Each row is multiplied by one more 2 than the previous row. So this row has 1 2, this one has 2, this one has 3, this one has 4, and then the next one has 5. And these 2's, this product of 2's, can be written in something called exponential form. And we're going to talk a lot in this unit about expressions, and some of them are going to be using exponents. Okay, so an expressions that multiply the same number over and over again are written using exponents. So it's very simple to write an exponent. You just look at how many of a particular number is being multiplied in a multiplication problem. So in row 2, there's only 1 2 there. So I would write 2 to the first power. In the third row, there are 2 2's being multiplied. So I would write 2 to the second power. In the fourth row, there are 3 2's being repeated. So the exponential form of 8 would be 2 to the third power. In the fifth row, there are 4 2's because 16 is made up by multiplying 2 times 2 times 2 times 2. So we could also say 16 equals 2 to the fourth power. And 32 is written with 5 2's being multiplied. So 32 can also equal 2 to the fifth power. Now you might be asking yourself, what is the exponential expression that equals 1? And again, we can look at a pattern to figure this out. Let's look. The base, or the 2, the number that's being multiplied repeatedly, has not changed from row to row. What has changed is the exponents. And if you'll notice, every time I increase my row number, I also increase my exponent by 1. So to figure out what row 1 would be, or 1 in exponential form, I can simply continue the pattern backwards. If I start at the bottom, 5 minus 1 is 4, 4 minus 1 is 3, 3 minus 1 is 2, 2 minus 1 is 1, and so my exponent for row 1 would have to be 2 to the 0 power, because 1 minus 1 is 0. And we're going to talk about this a little later on in the unit. But any base raised to the power of 0 is always going to be 1. Let's look at exponents a little more closely. Every exponential expression has a base and an exponent. The small number that is written in the top right-hand corner is the exponent, and in this case, 3 is the exponent. 5 is the base, and the base is the number that we multiply over and over, or repeatedly multiply. The base tells you what number to write down. The exponent tells you how many times to write that number. So we are writing 5 3 times. And always with exponents, we are multiplying. And 5 to the third power, which is 5 times 5 times 5, equals 125. If I look at exponents expanded out, the base was 5, the exponent was 3. The exponential form is 5 to the third power, and when we have a number raised to the third power, we sometimes call that cubed. So we could read this 5 cubed as well. The expanded form is the base written out however many times the exponent is. So 5 to the third power would be 5 times 5 times 5. And standard form is what we're used to seeing when we have a multiplication problem. That is, the final product is called standard form. Now it's your turn. We're going to go over an example together, and then I'm going to give you a table to try on your own in your notebooks. You're going to look at the table and figure out what is the missing entry. So in this case, what is the standard form? And I can look. The base is 3. The exponent is 2. So in exponential form, I would write 3 to the second power. In expanded form, I would write 3 times 3, because expanded form is the base being repeated however many times is indicated in the exponent. And the missing piece for this one is the standard form. So you would need to figure out what is the product of 3 times 3. And in this case, the answer is 9. Now in your notebooks, copy this table and complete it. Figure out what the missing entry is. Don't forget to WSQ. And remember, as always, you can go back and watch this video as many times as you need to, or just watch particular parts that are causing you a little bit of difficulty.